Hello guys, welcome back to the session. We are going to discuss about the part 2 of current electricity. In the last video we have seen about resistors, resistivity and so on. Now let us see how are the resistors going to behave when you are connecting them in series and parallel. So that's what we call it as a combination of resistors. Let us see the resistors connected in series first. For example, if I take a resistor say R1, another resistor of resistance say R2 is connected in series. Let us say maybe let us say one more, say maybe R3 is a resistance. Now if I just connect this to a cell like this whose potential difference or EMF is say V. Now what happens, this cell supplies the charge carriers. For example, here the current will be going from higher potential region to lower potential region like this. Now we know that the current that is coming through this way has to go through this, there is no other go. Then since current is going in the same path, so charge carriers cannot die somewhere in between, hence current will be the same throughout. Current will be the same throughout. So now you can just think of number of cars going from home, and then all the cars has to reach back to home. Okay, so whatever is the current that is going from the cell, the same amount of current should be reaching here. You can say each car has a kind of a charge. Now all these cars should be going all the way and then come back to the home again. So hence you can say that current will be the same in series. What is the take home message from this? Current is same in series. Now you can see that here whenever you are saying that V is the EMF of the cell, that means a higher potential plate is having V is the potential say, then lower potential should have a 0. The potential difference between this plate and this plate should be V. That is the idea. Now whenever there is a resistor or capacitor or inductor or any other device in between, then only potential increases or decreases or whatever, potential difference differs. But then here if you see in between here till here there is no any such component, hence till here potential is V. Here it is 0 means throughout this wire till here the potential is going to be 0 itself. Now you can see that potential V is becoming 0 in this path. That means what? Potential is getting distributed. Potential gets distributed in series combination. Okay, now if you see how much, you know that from Ohm's law delta V is equal to IR. So how much is the potential drop here? Let us see. Current you have seen that is I through this resistor, then the potential drop is going to be IR1 here. The potential drop here is going to be IR2. Potential drop here is IR3 with this logic. Right, now you have seen that potential gets distributed, that's what I said. So let us say the potential drop here is delta V1, here it is delta V2, here across R3 it is delta V3, let us say. So the essential potential difference delta V, total potential difference, is nothing but delta V1 plus delta V2 plus delta V3. So now what is the delta V1 here? That is IR1 plus what is delta V2? IR2. What is delta V3? IR3. Now instead of having three such resistors, if I have one single resistor whose equivalent resistance is say R equivalent. Okay, and now assume that you are connecting this to the same cell, then what happens? Current will be going in this path from higher potential to lower potential. The same amount of current should be given back to the circuit I, let us say. Right, V is the potential difference. Right, now if I just assume that here the potential drop across this is going to be delta V is equal to what? Current is I and resistance is R equivalent. Right, now can I say that is equal to IR equivalent? If I cancel, since all the currents are same, I gets cancelled on both sides, then R equivalent is equal to R1 plus R2 plus R3. Okay, so this is equivalent resistance of the cells resistors which are connected in series. Now if suppose if there are n resistors like this, then R1 plus R2 plus R3 is equal to Rn will be the when R1 plus R2 plus R3 and so on Rn will be equivalent resistance for such resistors combination. Now if suppose if you are connecting n number of resistors, each are having resistance or let us say, then equivalent resistance is going to be NR. Okay, so that's what is nothing but your series combination. Okay, let us see the resistors connected in parallel right now. So let us say there is a resistor of resistance say R1, another resistor of resistance say R2, one more maybe of resistance say R3, right? So if they are connected in this fashion, we call such combination as a parallel combination. Now here I am just connecting it to a cell the same way we have discussed in the last slide. So if suppose EMF is say V here, it has to be V and 0 is the potential at the lower potential plate. Now here since there is no capacitor or inductor or resistor in between, till here the potential will not drop. Here also potential is V, here also potential is V, here also potential is V. Here 0, 0, 0, 0 because again the same logic. Okay, so you can see that R1, R2, R3 are connected across the same potentials V and 0, V and 0, V and 0. That means in parallel combination, you can say that potential is same. In the previous case current is same, yes or no? Potential is same here, right? Now what is getting distributed here? You can see that from Kirchhoff's current law that we are going to see in the next slide. Now here whatever is the current, what did we discuss? Cell will be pushing the charge carriers. So let us say current is getting started here, I is the current. Now that current, just now I have told you that you can assume that these are nothing but a number of cars. So the number of cars which are passing through this, okay, there are three ways to go. That means some number of cars will go like this, some will go like this, some will go like this, depending upon the resistance. More is the resistance, less is the current. And hence here the current is I1, let us say, here current is I2, current is I3 because resistors are not same, resistance values are not same, hence current will not be the same here. If suppose resistance values are same, then the current values will be the same in each branch. Okay, so that's all. Now let us see current is getting distributed. Yes. Now what does it mean? I is equal to I1 plus I2 plus I3. So let us see what are the potential drops here. So here V minus 0, that is V is the potential drop. According to Ohm's law, can I say it as I1 into R1? Okay, so similarly I can say I1 is equal to V by R1 here. How much is the current here? Can I say it as V by R2? Here it is V by R3. Now these are the currents. I mean I1 is equal to what? The current that is passing through the resistor R1, that is V by R1. Here it is V by R2 through the second resistor. Next through the third resistor it is V by R3. Now see, if I consider the equivalent circuit diagram where instead of having three resistors, if I have only one resistor whose resistance is say R equivalent, and I am connecting this to the same cell or similar cell. So V is the potential difference between the two plates. Here V, here 0. So therefore till here the potential will be V and 0 is the potential till here. Okay, so again I can say that current that is passing through the cell is I. So since there is no other path, all the current will be passing through this R equivalent itself. Now can I say from Ohm's law, V is equal to I R equivalent. Now what is I? V by R equivalent. Now V by R equivalent is this. Now can I cancel all these V's? Yes. So then 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3, and I mean that's it. if suppose there are n number of resistors like this, then it is 1 by R1 plus 1 by R2 plus 1 by R3 and so on, 1 by Rn. That's your 1 by R equivalent. Now, if you have only two resistors, then R equivalent can be written as R1 R2 by R1 plus R2. Now, assume that n resistors of equal value of resistance connected in parallel, then equivalent resistance will become R by n, right? That's all about your resistors combination. Okay, let us discuss about electrical power and energy right now. Whenever you have got a cell whose EMF is V and there is a resistor connected to it of resistance R. Now, the cell moves the charge carriers in the circuit, the current is I, let us say. Now, the power can be defined as the product of voltage and current. Now, what is this voltage? According to Ohm's law, we can say that V is equal to IR. If I substitute that here, I'll get P is equal to I square R. Now, whereas if I take I is equal to V by R from Ohm's law again, I'll get P is equal to V square by R. Now, these are the three formulas for electrical power. Now, electrical energy is nothing but what is when energy can be written as power into time. Otherwise, you can say that power is nothing but rate at which energy is spent. Power can be written as rate at which energy is spent or rate at which work is done and so on. So, D is equal to P dt or whatever, and hence energy is equal to power into time. Now, electrical energy E can be written as I square RT, where T is nothing but time, and P is equal to V square by R into T. Otherwise, sorry, this is energy. Now, other one, another one is PE is equal to value ratio of technology, not bit. It's voltage into current into time. Okay, so these are the three formulas that is for electrical energy. Okay, now let us talk about Kirchhoff's current law. Now, if suppose if there are some three wires connected like this, let us say current that is passing through this one is say I1, and the current that is passing through this is say I2, current that is passing through it is say I3. Now, this is called a junction. What is junction, by the way? Junction is nothing but minimum. It is a location where minimum three wires should be meeting, not two wires, three wires. So, if three wires are meeting, we can call this as junction. At any junction, the sum of algebraic sum of incoming currents are equal to sum of outgoing currents. Another way of saying the same thing is summation of all the currents at a junction is equal to 0. So, what does it mean? Here in this situation, you have to consider that incoming currents, if you assume them as positive, then outgoing currents will be negative. Outgoing currents are negative. So, you can see that here, what are the incoming currents here? This is incoming towards the junction. These two are outgoing currents. So, I can say from this, I can say that as I1 is equal to I2 plus I3. Otherwise, if I use this, I can say what are the incoming currents? I1, if I take that as positive, and I2 and I3 are outgoing currents. They should be negative. I hope the point is clear. So, the same thing, I1 is equal to I2 plus I3. That's what you get. This is what we call it as a junction rule also, because we are talking about a junction here. Understand? We also call it as Kirchhoff's first law. So, it is based on law of conservation of charge, because you can see that like charge is always what is the meaning of law of conservation of charge? Charge can neither be created nor be destroyed. It can only be transferred from one body to another body. So here the charge is a constant. If I talk about total charge, sum of all the charges equal to constant, then I can say it is nothing but if I take differentiation of it, dq by dt is equal to differentiation of a constant is 0. So what is this? Current. Sum of all the currents at a junction is equal to 0. Hence we say that it is based on law of conservation of charge. Is that clear? Yes. Now let us talk about Kirchhoff's voltage law. We also call it as a loop rule. Okay. Why do we call it as loop rule? Let us see. Now if you just talk about a loop, let us say there is a resistance here, maybe one cell here, one more resistance, or maybe like one more cell like this, and so on, of resistances R1, R2, E1, E2, EMFs, let us say. Now we are going to consider a loop here, and the loop can be clockwise or anti-clockwise. You can take any way, no issues. But only thing is, first of all, you have to select the current. Assume that E2 is greater than E1. Then let us say current is going like this. I current is going like this. You have to define currents first in order to solve this. After obtaining the currents values, then I can take either clockwise or anti-clockwise. I am taking it as clockwise right now. If I take that, remember, you have to assume that wherever you are starting, let me say, just for the sake of understanding, I am calling it as A, B, C, D, A. Loop means wherever you are starting, you have to get back to the same location again. If you are starting from A, get back to A. Starting from B, get back to B, and so on. That is what is called a loop. Now I am starting my journey from here. All the way I have to come back to this location. Now I started moving on my path in this way. Now you have to remember that potential drops in the direction, whenever there is a potential drop, then delta V, you have to consider it as a positive, potential drop means negative, potential drop is a negative. Whenever there is a potential rise, then you have to consider delta V as a positive. Now try to see this. Now I started moving myself in this path now, like this. So when I reach this location, you can see that current is going from here to here. Current always go from higher potential region to lower potential region. So this is a higher potential region and this is a lower potential region. That means on your path you are going from high to low potential. That means you are going from high potential to low potential. Hence it is potential drop. So it is negative. Okay. So on your path you are going from, this is higher potential plate and this is a lower potential plate. So you are experiencing potential drop again. So then it will be negative. Now again you are going this way. So here the current is going like this. This is higher potential, this is a lower potential. That means potential is dropping again. When you are going from high to low, hence potential is dropped. Now on your path you are going from lower potential to higher potential plate. That means you are going from lower potential to higher potential. Hence I have to consider it as a positive now. Okay, is that clear? Okay. In fact, you can take anti-clockwise as well, no issues. So if I just talk about this Kirchhoff's voltage law, that is summation over delta V is equal to 0. I can say that the algebraic sum of all the potential drops in a loop is equal to 0. Okay. So sum of all the potential drops in a closed loop. This has to happen in a closed loop. Okay. Now I started my journey from A. So let me just write along my path I have experienced some potential drop here. How much is that? According to Ohm's law, IR1 is the potential difference. Whether it is drop or gain, I have told you already. Now you are going from higher potential to lower potential. Okay, higher potential, lower potential, it is a drop. Next, you are going from again higher to lower, again drop. How much is the potential drop there? E1. Okay, now our potential difference is E1. Next, you are again going from high to low, hence potential is dropped. How much? IR2. Next, you are going from low to high, potential gain. How much? E2. And that's it. You have come back to this location. Hence, these are all the potential drops in a total closed loop. hence it has to be equal to 0. And that's how you'll be applying KVL, Kirchhoff's voltage law, to a given loop. Now if suppose you have got open circuit like this, maybe something like this, okay, I'm taking this point as A, I'm taking this point as a B, resistors, say R1, say R2 here, E1 and E2. How do you apply KVL? And let us say you have been asked to find out the difference between, potential difference between A and B, maybe VA minus VB. How do you find this? Okay, the trick is again you have to take the loop. First of all, you decide the current. I am assuming that again E2 is more than E1. So current will be going like this. So all the way current will be going back to the cell of the same value I. Okay, that is the current. Now wherever I start my journey, I have to, this is how you will be defining the current first. After defining the current, you have to choose the path. I am choosing the path from A to B like this, A to B. Now I started moving from A to B. Wherever I start, potential is high, potential is positive. Wherever I end up, potential is negative. In between all the potentials you have to write in the using Kirchhoff's voltage law. Now I am moving this way. That means I am going from higher potential to lower potential. Okay. So what does that mean? Potential is dropping, high to low. Dropping means minus. How much is the drop here? Current into voltage, current into resistance, I R1. Now here you are going from high, I am going from high to low. Hence it is potential is dropped. How much? E1. Now again current is going this way. Here higher potential, here lower potential. Potential is dropped again. How much? IR2. Next, here you are going from low to high. That means you are gaining the potential. That means potential rise. How much? E2. And that's what it is. If I want to write VA minus VB, that's what is being asked. That is going to be IR1 plus IR2. I'm taking that I common. Then if E1 goes to other side, becomes plus E1, E becomes E2 becomes minus E2, and that's it. This is the answer for that question. I hope you got clearly how do you apply this KVL. We call it as Kirchhoff's voltage law, and this is actually law of conservation of energy. So this KVL is based on law of conservation of energy. Yeah, let us discuss about the electromotive force and internal resistance right now. Every cell has some internal resistance, say R. Now, so in general, when you are not connecting the cell into any circuit, then the potential drop is E itself. But then when you are connecting it to circuit, then what happens? The circuit cell starts offering some amount of internal resistance. Okay. Now let us see the same thing. If you consider, let us say for example here A is the point and B is the point. Let us say I am applying KVL here again. Okay. So let me see the potential difference between A and B. VA, wherever I start, I have to have potential VA, and wherever I end, potential is minus VB, and that should be equal to 0. That is your Kirchhoff's voltage law. Now on my path, I started moving this way. Okay. So on my path, I can see that I am experiencing some potential is dropped. I am going from high to low. Hence minus E, and current will be going from higher potential to lower potential. No? So here this is the current. Now current is going here like this, means it is higher potential. Here it is lower potential. But I am going from low to high. Hence it is plus IR. Now if I just find out the potential difference between the two terminals of a cell, that is VA minus VB, and that's equal to E minus IR. Okay. So you can see that whenever actually you have bought a cell of EMF, let us say E, but it doesn't offer E voltage or potential difference, but it will be offering some amount of less value. For example, you are buying a cell of 2 volts, it will never give you 2 volts when you are connecting it to cell. That means some voltage, for example some 0.5 voltage of potential drop will be there because of internal resistance. Hence we can't get perfectly the 2 volts. Okay, so therefore you can say that EMF is nothing but electromotive force or potential difference when current equal to 0, or I can say it is a open circuit when there is no current existing in the circuit. Whereas wherever there is a current, then potential automatically decreases by IR. Okay. Now the potential difference delta V can be written as E minus IR. Okay. So this is the difference. This is what is called EMF, where R is nothing but resistance, internal resistance offered by the cell, and that is because of materials used in materials of electrolyte used in cell preparation. So delta V is nothing but a potential difference. So I hope you understand the difference between potential difference and EMF. So what is the difference between EMF and potential difference? That is this is when we define when the circuit is an open circuit, and it is when there is a current flowing, or you can say closed circuit. Clear? Next, when the cells are connected in series, you can have one cell which has a resistance say R1, internal resistance R1, and EMF of say E1, and another cell of EMF E2 and internal resistance say R2 are connected in series. Okay. Now if I just apply KVL, so just now we have seen that wherever I am starting my journey, okay, I have to get a plus potential, plus potential. Wherever I am ending, the potential is minus, okay, minus VB, and the total potential difference has to be 0. Now if I just start from here, I can see that I am going from higher potential to lower potential. I am going in this path. This is the path direction. Okay, so I am going from high to low. Hence it is potential drop is E1. Potential is dropping. Now that's why minus. Now here you are going from low potential to higher potential because current was going like this. Okay, so you are going from low to high. Hence positive is the potential drop, potential rise, you can say. Now you are going from high to low, minus E2. Now you are going from low to high, plus IR2 minus VB is equal to 0. So VA minus VB is equal to what? That is E1 plus E2. Now if I just take these two things common, and they are minus actually after sending them to our other side of equal to, then I can write it as I into R1 plus R2. Now instead of having the two cells, if I have only one cell which has EMF say E equivalent and internal resistance say R equivalent, then again if I just apply the same thing, I will get let us say this is A, that is B now. So VA minus VB will turn out to be E minus IR. Just now we have discussed in the last slide. This is E equivalent minus IR equivalent. Right? Now if I just compare these two things, I can say that E equivalent is equal to E1 plus E2. In case I have got a lot of such cells connected in series, then it is E1 plus E2 plus E2 plus and so on En. That is equivalent EMF. Now if I compare this with this one, I will get R equivalent is equal to R1 plus R2. If there are n such cells of resistances R1, R2, R3 and so on till Rn, that's how we will be getting equivalent resistance when they are connected in series. Clear? Let us discuss about the cells connected in parallel. Now you can see that, let us say if I take there are two cells of EMF E1 and E2, and the resistances, internal resistances say R1 and R2 are connected in parallel. You can see that. Now if I apply KVL in the path A, P, Q, B, then the potential difference, let us say potential at A is VA and potential at B is VB. I started my journey from here and I will be ending up somewhere here. That's why ending up location is minus and starting location is positive. Okay. So here along my path I am experiencing potential drop. I am going from high to low, so potential is dropped minus. Now current is generally going from higher potential to lower potential. Let us say this is I1, sorry, this current is say I1 and this current is say I2. Okay, so current is going like this, that means you are going from high, sorry, 1 minute. So current is going like this, this is high potential, this is low potential. So you can say that current is you are going from low to high, hence potential is gain. How much is the gain now? That is current is I1, resistance is say R1, okay, and that's it. Now from here, if I get what is the current, I1 is equal to, one more step, let us say, if I take VA minus VB, VA minus VB is equal to what? That is E1 minus IR1. So I can say this is VA minus VB is what? I am taking it as a V now, just for the sake of easiness, and that's called terminal potential difference. So what is I1 from here? I1 is equal to E1 minus V by R1, isn't it? Similarly, if I apply the KVL at AX by B, then I get VA, since it is a starting point positive, termination point is minus. So now I am going from high to low, so potential E is dropped. Now here current is going like this, that is I2, okay. So you are going from low to high again, so potential is gained, IR2 minus VB is equal to 0. So can I say, if I just apply the same thing again, I can similarly prove I2 is equal to E2 minus V by R2. Now you know one thing for sure, here I1 is the current coming here, I2 is the current coming here. Can I say it is current I? Yes, I can say. Now I is equal to I1 plus I2. That means at this junction these two are incoming currents, I1 plus I2, and that's equal to outgoing current I. Okay, so here let us substitute I1 and I2 in this equation. What is I1 here? E1 minus V by R1. What is I2? E2 minus V by R2. Okay, so if I rewrite this, I can get this as E1 by R1 plus E2 by R2 minus, if I take V common, I get 1 by R1 plus 1 by R2. Right. Now if I just take this to other side, I get V into 1 by R1 plus 1 by R2, and that's equal to E1 by R1 plus E2 by R2 minus I. Now if I just take this 1 by R1 plus 1 by R2 to other side, I will get V is equal to this by 1 by R1 plus 1 by R2, and this by 1 by R1 plus 1 by R2. If I take an equivalent cell whose EMF is say E equivalent, whose resistance is say R equivalent, which can do the same job for us. Now I can write this as V is equal to E minus IR. If I just otherwise I can say E equivalent minus IR equivalent. Now if I just compare this with this, I will get E equivalent is equal to, what is that? E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2, right? So what about 1 by R equivalent? So I can write this as by 1 by R equivalent. If I just compare this with this, I will get 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So this is how you will be finding out the equivalent EMF and equivalent resistance when they are connected in parallel. Okay, let us see the last slide of this current electricity part. Now you can see that it's a very important question for CBSE level, Wheatstone bridge principle. So basically we are talking about balanced Wheatstone bridge condition. So you know that when the resistors are connected in this fashion, we call it as a Wheatstone bridge. Now let us say R1, R2, R3, R4. Oh, this is R4, sorry. This is R4. So there are 4 resistors connected like this, and 1 resistor in between connected like this. And we also can take sometimes as a galvanometer here. So it's also kind of a resistor. Okay. every device offers some resistance, right? So that's what I am calling it as R5 now. Now whenever the bridge is in balanced condition, then the current through this R5 or galvanometer will become 0. When the current becomes 0, you know that when there is no potential difference between both the ends will become will give you the current 0. That means what? Here x and y should be at the same potential. Let us say Vx should be equal to Vy now. Okay. So now if I split the current I that is passing from the circuit will be becoming I1 and I2 at this junction. Now since there is no current passing through it, all the current will be going like this. Now I2 is the current. Since the no current is going like this, then current will be I2 here also. Okay. So again both these currents I1 and I2 will give you again I know. I is equal to I1 plus I2. Now if I apply Ohm's law, let us say in this branch, I can say it as V minus Vx is the potential drop between these two ends of a resistor. So now what is the current that is passing through it? That is I1 and resistance E is R1, right? Now if I apply Ohm's law in this branch, I will get V minus Vy is equal to I2 R2. Okay. Now if I apply the same thing here, Ohm's law, that will give me Vx minus potential at this location is 0. So Vx minus 0 is what? I1 R3 IR. Current is I1, resistance is R3. Clear? Now it is Vy is the potential here. Here potential is 0. Vy minus 0 is equal to I2 R4. Now if I use that Vx is equal to Vy here, I know that this potential and this potential will be the same. Can I say, then V minus Vx is equal to V minus Vy. Then I can equate these two things, isn't it? Since Vx is equal to Vy, I can take this, let me call this as equation 1. Say this as equation 2, equation 3, equation 4. So if I take equation 1 and 2, I will get I1 R1 is equal to I2 R2, because left hand sides are same. I can equate right hand sides. Keep it aside. Now if you look at this is Vx minus 0 Vx, this is Vy minus 0 Vy. Since Vx is equal to Vy, so both these left hand side terms will be the same. I can write this as I1 R3 is equal to I2 R4. So can I say from this, what is I1 by I2? That is R2 by R1. Now what about this? Again I1 by I2 is equal to R4 by R3, right? Now you can see that again left hand sides LHS are same, so you can equate RHS. So I can say R1 by R2, I am making it ulta, R1 by R2 is equal to R3 by R4. This is the condition for balanced Wheatstone bridge, and this is very important question for board level, which will be given for 5 marks or 3 marks. Okay. So with this we have completed current electricity chapter. So we are going to see the next chapter in the next video. Okay. Thank you.